Hi everyone, welcome to Quick Calculus with Professor Monty. Today we're talking about partial derivatives. Now partial derivatives are when you're taking a derivative but you have more than one independent variable. So what I've done here is I've written a function in two different ways. On the left, that f of xy equals 3x plus y to the fifth, that's written in what we call Newton's notation. And to the right, it's the same function, but written in Leibniz notation. And I just want to show you the two ways so that you can get used to either format. Okay, when I take a partial derivative, what I'm doing, I'm trying to make one variable change and the other one stay constant. Because I want to know what happens, for instance, if x changes, what happens to the function? Well, we don't want y to change and confuse things. So to say that we're taking the derivative but only x is changing, in Newton's notation, we write it as f sub x. That's the partial derivative of f with respect to x. So we're taking the derivative, x is the variable, so the derivative of 3x is 3 just like it always is. The tricky part is when we look at that y to the fifth, there's no x there, so y to the fifth we treat as a constant. So since it's all by itself, when we take the derivative of constant, we just get 0. And so the partial derivative with respect to x is just 3. Let's do that again, but showing it in Leibniz notation. So we'd say the partial derivative of z with respect to x, so it looks a little bit different. But again, think about what we're doing. We're letting x change and y stays a constant. So the derivative of 3x with respect to x is just 3, but the derivative of y to the fifth, again, it's a constant, so it's just 0. So again, different notation, same result, of course. We get 3 as our answer. All right, let's make it a little more complicated. So here's another function I've written down. This time we've got x's and y's both in the same piece of the function. So when I take the partial with respect to x, think of what's happening. If I just had 2x, it would stay there because a constant multiple stays. Well, that y squared's also a constant multiple, so it's going to stay. Now, what I like to do when you're first learning it, think, okay, the 2 is going to stay, it's a constant multiple. The derivative of x is just 1. The y squared stays again constant multiple. And if I do the same to the next piece, the 4 stays, but the derivative of x to the third, 3x squared. And the 4 stays because it's constant multiple, same reason the y to the 6 stays. And so what I get when I clean that up a little bit is I just get 2y squared minus 12x squared, y to the 6th. That's my partial with respect to x. Let's look at it with respect to y. So now what I'm going to do is I'm going to take that same thing, but we're going to write it partial with respect to y. This time the 2x stays because it's constant multiple, and I get the 2y for the derivative of y. And similarly, 4x to the third, the derivative of y to the 6th, 6y to the 5th. And then just multiply things out, combine those a little bit, and I'll get my partial derivative with respect to y is 4xy minus 24x to the third, y to the 5th. And let's do that again in Newton's notation, or rather that was Newton's notation. We'll do it in Leibniz notation. And this time we'll try to go a little bit faster. So instead of writing, for instance, the 1, let's see if we can do it where we just take the derivative and multiply coefficients times exponents at the same time. So the partial derivative with z with respect to x. Now going back to x being the variable. Well, just like if it was 2x, the x would go away. The x is still going to go away. We're going to get 2y squared. And then just like if we had 4x cubed, I'd do the 4 times 3 is 12, x squared. I'm going to do the same thing. But remember, 12x squared, the y to the 6th is a constant, so it just stays. Constant multiples stay. If I was just adding or subtracting a constant by itself without the variable, that's when it goes to 0. And then the partial of z with respect to y, now we go back up to the original problem, the 2xy squared, bring the 2 down, the 2 exponent for the y squared is going to multiply by the 2 in front, give us a 4x, but now it's just y to the first. And then the 4x cubed stays, times bring down the 6 from the y to the 6. That's going to give me 6 times 4 is 24. X to the third, y to the fifth. And we can compare that to our answers we got when we did it in Newton's notation. We see, of course, we get the same answer, but we just go through it a little quicker. If you need to go slower like we did before, absolutely do that to learn it. But if you can get to the point, and some people get to the point real quickly where you can just do it in your head, definitely do it that way. But that's the idea. Hope it helped. If you like the video, go ahead and subscribe to my channel. And if you have any suggestions for other videos you'd like to see, just drop me a note in the chat, and I would be more than happy to make those. All right, that's it. Best of luck to you. And remember, you can do this.